So this was the problem from the lab, the refraction lab that we use the lasers. It says a tank holds a layer of oil of thickness 1.65 meters. So that's telling me that this distance right here is 1.65 meters. It says that floats on a layer of SERP of a thickness of 0.830 meters. So this is 0.83 meters thick. And then it says, as shown in the figure, both liquids are clear and do not mix. A light ray originating at the bottom of the tank at some point P, so this is point P right there, okay, at some point P, crosses the oil SERP interface at a point 0.9 meters from the axis. So what that means is this distance is 0.9 meters. The ray continues and arrives at the oil air interface, so that's this right here, 2 meters from the right of point P, and at the critical angle. What is the index of refraction of the SERP? Now, if it's happening to be approaching this surface at the critical angle, let me make this a little larger so we can see it. If I'm approaching the surface at a critical angle, what that means is that this angle is at just the right angle that the light that's leaving this, if this was a light right here, then bends 90 degrees. Okay, that's what the critical angle is. So the critical angle means that when I come out of the medium, and remember, in order for you to have a critical angle, the medium you're going into, so N2, has to be a less index of refraction than the medium that you're in. And in this particular case, this is talking about this little boundary right there. So in order for me to bend exactly flat, or in this case 90 degrees, the stuff I'm going into has to be less than what I'm currently in terms of the light ray. So that critical angle is happening right there. So what we know about critical angle is that sine of the critical angle is N2 over N1. So I can use that relationship, or that comes from Snell's law, which is N1 sine theta 1 equals N2 sine theta 2, where N1 and sine theta 1 correspond to the current substance I'm in, and this is the substance I'm going into. So that's what we get this relationship right here. So here's the thing. Through geometry, we can actually find this angle right here. So what I'm going to do is I'm just going to extend the normal all the way down. Okay, so there we go. I know that this side right here is that subtracted from that. So that side right there is 1.1 meters. All right, we also know that this side is 1.65 meter. So if I want to find that angle right there, take a look right here. This is the opposite side to that angle, and this is the adjacent side. So TOA is what I'm going to use here. So I'm going to say tan of that angle up here, so that angle right there, tan of that angle, equals the opposite side, which is 1.1 meter, all over the adjacent side, which is 1.65 meter. And so I'm able to actually find that that angle if I do this. So I'm going to get my calculator out here, and I'm going to go ahead and do the inverse tan. So I'm going to find the theta by doing the inverse tan of that stuff right there. So the inverse tan of 1.1 divided by 1.65, and I get 33.7. So the theta is 33.7 degrees. That's my critical angle because that's this angle right here. So what I'm going to do is I'm actually going to solve for N1. N1 is the current medium that we're in, and we're trying to get out into air at the top. So we're talking about this right here is occurring at that boundary. Okay, so N1 would equal N2 over sine of the critical angle. So N2 is just air, so that's 1. Sine of the angle we just found, because it says it's the critical angle, 33.7. So 1 divided by sine of 33.7, I get 1.8. So 1.8 is the index refraction of what we're in 1. Now this corresponds to the oil, because what we're talking about is oil into air. This is air right here, and we were in oil. Now if we work backwards, let me erase some of this stuff here. Okay, if we work backwards, this angle that we just found right here, that angle right there of 33.7 degrees, that is that angle right there, 33.7. And we know the index of refraction of the oil is 1.8. Okay, So then what I'm going to do now is I'm going to say, all right, well, this is the angle that I'm approaching that boundary. And so here we go. Here's my light ray. Bam, hits that boundary. It bends towards the normal like this. Okay. And so we could tell right now that whatever this SERP's index refraction must be less than the oil's index refraction, because as I enter the oil, I bend towards the normal. And when I bend towards the normal, I'm slowing down. Remember, slowing down, okay, is towards the normal. That's how it's going to bend when I refract. Okay, so I know that angle is 33.7 because that boundary and that boundary are parallel, right? I have a line intersecting it, so that angle and that angle. You've learned that in math class. We know the index refraction of that. So now we just need to find that angle. How do I go about determining that angle? Well, I know this side right here is 0.9 meters, and I know that this side is the 0.83 meters. So to find this theta, I'll call it theta green. Theta green would be tan of that theta would be the opposite side, so 0.9 meter, all over the adjacent side of 0.83 meter. Meter will cancel, and so if I want to get that, I will take the inverse tan of all that stuff. And so if I do that, I do the inverse tan of 0.9 divided by 0.83, and I get 47.3. So the angle that I get for the green is 47.3 degrees. All right. So what I'm going to do is I'm going to say, hey, I'm first in this substance. So at this boundary, I can write Snell's law again. So n of the syrup, or I can call it n1, sine of theta when I'm in the syrup should equal n of when I'm in the oil times sine of theta in the oil. And so because I'm going from syrup into oil. So this is what I'm looking for. I'm looking for n of the syrup. That's what the index refraction of the syrup. So n of the syrup would equal n of the oil, which we've already determined, sine of the angle that I enter the oil, all over sine of the angle I leave the syrup. So we said that was 1.8, sine of the angle of the oil, which was 33.7 degrees, all over sine of 47.3 degrees. So if I do 1.8 times sine of 33.7 divided by sine of 47.3, I get about 1.36. So 1.36 must be the index of refraction of the syrup in order for all this to happen. The key idea is that it leaves the oil boundary at the critical angle. And so what that means is the light ray will bend parallel or right down the surface. Critical angle means that's the minimum angle to create this 90 degree bend right there. So try that out again and see if you can figure that out.